All right, so grade 12s, welcome back. And I'm sort of rambling in that last video with explaining what these electromagnetic waves and everything else. But let's just do some notes and we'll finish off this part of the course. And okay, so I just want to settle the score with Huygens. These staples stuck to my pen here. So, summary. Let's summarize. Okay, Huygens. Okay, 1. I'm going to write Huygens versus Newton. I'm just going to give myself a little more space. Huygens and Newton. Okay, so I'll make a little table here. Speed of light in speed of light is less in dense media. So score 1 for Huygens, false. So this in the 1800s. Okay, this is how it all came together. 2. Light shows interference in Thomas Young's famous experiment, right? Double slit experiment. Light shows interference of waves. Score 1 for Huygens, false. And this one's really like key, big time. Okay, that's a big problem for Newton. That one there, you can't explain that with a particle model. Okay, 3. Light propagates in a vacuum. Okay, so yes for Huygens now in the 1800s. How? By EM waves. Okay, so no ether, like he thought. That was it was sort of his biggest blunder. But what else? He didn't know about all the stuff about electricity and magnetism. He didn't have the benefit of that knowledge. Now, actually, Newton could explain this. That's one thing in favor of his theory. He could explain that. But anyway, the result was, what is light? Light is a self-propagating disturbance in electric fields that surround all charged particles. Okay, now not getting into the precise details. That's like a second-year university course of the whole electromagnetic wave model. But they figured a bunch of things out. It's really quite amazing. Okay, and I'm just going to say that the EM wave theory was considered the greatest theory ever at the time. And I'm just going to say why it correctly predicted. Results. Experimental results. In countless experiments. And led directly to the modern age in the hands of engineers, right? See, the job of a scientist is to sort of come up with the explanation. Here's how you explain the connection between electricity and magnetism and light. Then you give that to an engineer and they build things with it. They make things with it. They just design things with it. Okay, and that's what engineers do. And so, you know, think of all the things that have been designed and made by these guys over the past, 150 years or so. It's really quite incredible that society has been completely transformed in this time. Okay? So, this is honestly the electromagnetic wave theory. Scientists were confident. Okay, physicists were confident in saying that all questions that soon all questions would be answered that anyone had ever asked about science, or about like the world, about the universe. What was missing at the time they were working on atomic models. Plum pudding, okay, remember all this from your chemistry class, the plum pudding model, the Dalton's theory, and so on. Okay, so that's going on here as well. This is crucial. Okay, this is crucial because for the next unit, this is crucial. They felt like, all right, as soon as we get this one sorted. Now, here's the thing about, there's a connection between atomic models and light. So we know that light comes from atoms. That's where light comes from. So like, for example, when you turn on a light bulb, it's the atoms in that light bulb that are emitting the light. So how do they do that? Okay, so that your atomic model has to explain this. And that's where we're going next. Okay, and it turns out that this question with the atomic models led us down like basically a path basically to Wonderland. In other words, like down the rabbit hole, literally. Okay, because trying to figure out how atoms emit and absorb light is a very strange business for sure. Okay, so that's what the quantum unit is all about. So that's why it picks up right where this one leaves off. All right, I just want to show you a couple of pictures. Okay, and then we're pretty much done for today. So propagation of an electromagnetic wave. So this is how we visualize it sometimes. So here is a spark, something here where the charge is accelerating up and down. Okay, I'll just highlight it. So here's a charge going up, here's a charge coming down, like the demonstration I showed you. And then here we see the red electric field changing, and the blue is a magnetic induced field that also comes along with this disturbance. We see that they're transverse waves. Okay, and that's why polarization experiments work. And they travel out from the disturbance in this manner, okay, at the speed of light. So here they will travel at the speed of light, 3.0 times 10 to the 8 meters per second in a vacuum or in air. Okay. Now, we've also discovered a bunch of invisible radiation because of this theory, and partly because some of these things were discovered by accident, but we've discovered a broad spectrum of radiation, all electromagnetic. Okay, and here's the complete list. Radio waves can be hundreds of meters long. Okay, those are AM radio stations, which nobody really listens to anymore. FM radio stations go from 1 meter down to a few centimeters in length. Okay, radar and so on in centimeters as well. Microwave would be in here. Okay, I used to think microwaves would be around 10 to the minus 6 meters, but that's actually more of the infrared spectrum. But you get close with microwaves. Okay, so microwaves like probably in the millimeter range. Okay, millimeter down to close to micrometers. Okay, anyway, 0.01 centimeters, so now we're into fractions of a millimeter down to about 1,000 nanometers, that's infrared. And then the visible spectrum, which I've zoomed in for you here, goes from around 750 nanometers down to around 350 nanometers on the other side. Some numbers vary, but I would say that you could see shades of violet a little further down here to 300 nanometers or so. Okay, but look how narrow that spectrum is. That's all you can see. So this, right, is the visible spectrum. and that's all you see. Now, most of what the sun emits is there. Okay, so I mean, you might say, well, how useful would it be for us to see radio waves? Well, for a creature that evolved naturally on this planet, for us to have eyes that see waves that don't exist in nature, okay, would be kind of strange, right? Like, so for example, infrared light does exist in nature. Same with ultraviolet light. We know the sun emits some ultraviolet light. And there are some animals that can see infrared and that can see ultraviolet, okay? We're not one of them, but there are some animals that can see that. Now the sun emits some infrared and ultraviolet light, but it does not emit any X-rays, and it does not emit any gamma rays. So for you to have eyes to see that kind of radiation wouldn't make any sense. I mean, it's just not in the natural world. Like, sure, we have a device that emits X-rays, but your eyes could never see them because they're just not evolved to see something like that, okay? Because like that radiation doesn't exist in the natural world, thankfully, because it was out there all the time. It's ionizing radiation, right? So it's harmful to us. Radio waves, on the other hand, the sun does emit radio waves that we don't really detect here on Earth. And so again, it's not in our natural environment. And we've built radio waves now, okay? Like we built radio transmission towers on our cell phones and stuff, but you don't see the radiation coming out of your cell phone. It's there, but it's invisible, okay? And it is very high frequency radio waves, so somewhere around here for your cell phone. So I'm just gonna write cell phone technology somewhere around there, very close to microwave radiation. Okay, and yeah, you can't see the radiation, it's there, but again, not in the natural world. Like, what use would it be for an animal to develop the ability to see radio waves if there just aren't any radio waves out there for it to see? Okay, we've even seen examples of animals that live in caves where it's completely dark all the time, and they don't have eyes at all, right? So just so you know, like, the ability to see something depends largely on the environment that an animal lives in, okay? So the sun emits mostly visible light, okay? And our eyes are tuned to that. Makes sense, okay? Because the sun is what illuminates our world and allows us to see things in the first place. So anyway, there you go. That's the electromagnetic spectrum. So guys, that's it for the waves unit. I just want to show you where we are on the homework. Anyway, I think this unit is really cool. I love electromagnetic wave theory. I think, like, you know, this amazing thing that these guys figured out that changed the world. Like, their theory changed the world in so many ways. It's really quite profound. Okay, so now we have finished that. All done. Okay, now we're not going to do this right now. Okay, so we're not going to do those things. We will do the quantum unit. I'm just going to show you from last semester. I haven't posted it in yours yet, but I'll show you from last semester what the quantum unit looks like, just to show you how short it is. Okay, so the quantum unit, okay, is just a few lessons like this. We're not going to do radiation and radioactive decay. That was in the independent unit. It's 6 lessons. That's all. Okay, and you can get rid of this. We're not doing that. Okay. All right, so guys, that's it for today. There's only 5 lessons left in the course. We'll pretty much finish it. We technically have 2 weeks left, but we'll finish before that. We'll have a test, and that'll be the last thing. No exam, but we'll have a test on this. Open book test makes it easy because all this theory stuff you can just have right in front of you, so it makes it easy. So hopefully that'll give you a little boost. All right, that's it for now. Enjoy your weekend. We'll talk to you soon.